So, first thing we need to have a look at is the three types of calculation. As I said, there are only three. Although momentum questions in exams can look remarkably different, there's actually only three types of question. Okay? There are two where momentum is conserved. It might be worth making like a little list in the corner of your page here. So here's our route map for where we're going today. There are two types of question when momentum is conserved. They include collisions and explosions. Okay? So two of the types of calculation that you can do in momentum are related to when momentum is conserved. If you remember, when we talked about conservation of momentum, we said it's not always conserved. It's like not like conservation of energy, which is always conserved. Conservation of momentum only sometimes. So there are two types of calculation you can get when momentum is conserved. One is called a collision and one is called an explosion. And if you think about it, they're actually the same thing in reverse. There's then one example of when momentum is not conserved. This is where it's different to energy. All right? Any GCSE question where you use energy, you'll be using the idea that it's conserved. All right? In momentum, you've got to think a bit harder. This is why this is towards the end of P2. These are always the harder questions. Is because you've got to be sure you're doing the right thing. The way to deal with momentum not being conserved is with a quantity called impulse. Okay? And I'll explain a bit more about that when we get to it. Okay? So that's the good news in this section. It is a difficult piece of physics. It's harder questions, etc., etc., etc. Look at every single question, no matter what the topic, no matter what the setting, skateboard, whatever. Either momentum is being conserved because it's a collision, momentum is being conserved because it's an explosion, or momentum is not being conserved, and we're going to use the idea of impulse. Okay? If you get that bit right, you'll hopefully be able to get nearly full marks. Okay? Let's do number one then, which is a collision. All right? I'm not going to write massive notes about it, because actually all you need to be able to is to do it, and if you've got one good example in your book, we can practice some others, and that's how you'll be able to do it. So let's do a very simple example. Let's have a couple of railway trucks or something. There we are. Here's the situation. You've got a 4 kilogram truck moving at 10 metres per second. It bashes into a 1 kilogram truck that wasn't moving. There's an enormous explosion, obviously. No, not an explosion, sorry. There's an enormous collision. What will happen then is they will stick together. And you might think, well, you've never seen every exam question. How do you know? Well, if they don't stick together, then it's an A-level question. All right? If you read your specification, they're limited to these three because of the way the specification is set out. If they don't stick together, you've then got a much more complicated question, which they're not setting at GCSE at the moment. Okay? So I can promise you they'll look like that. It might be cars, it might be bicycles, it might be hedgehogs, it could be anything. Fundamentally, it's a collision. Two things come along, stick together, move off together. All right? The question is generally to work out at what velocity will they move off together. Okay? You might know from common sense that it's going to be less than 10. If you're going along at 10 and then you sort of couple up with something else that's a bit of weight in front of you, you're obviously going to slow down. You're not going to speed up. Okay? Now, what we're going to use then, remember this is a conservation of momentum type question. So if you're doing a collision, collisions are based on conservation of momentum. So that's the sort of guiding piece of physics that's going to cover the whole question. How are we going to do this question? The answer is we're going to conserve momentum. We don't conserve energy. If you work out the kinetic energy before and afterwards, it won't necessarily be the same. But that's the value of momentum. In things like collisions, it will give you the right answers. Okay? Now, let's work out momentum before. Momentum, really annoyingly, has the letter lowercase p. That doesn't really come up in the exam, but just in case you see it in the book or something. I've no idea why. Let's work out momentum before. We have got 4 kilograms. Don't sit there watching thinking, oh, this is easy. Yeah, it is now. But the night before the exam, when you open the book and think, how did you get the answer 27? Write it down, all right? Set it out so that you've got one there. You are writing this to yourself the night before the exam, so make it nice and clear. 4 kilograms is the mass and 10 metres per second is the velocity, all right? So the momentum of this one is pretty obviously 40, 4 times 10, kilogram metres per second. Yeah, it's an absolute mouthful, the unit. You might think that's been redefined to be called the something or the what's name, but it hasn't really. So the unit, I'm afraid, is kilograms, not per metre per second, because look what you're doing, you're timesing mass by velocity. So kilogram metres per second. I sometimes put a dot between the kilogram and the metres, largely to stop myself putting a diagonal line. So it's kilograms times metres, kilograms metres per second. Okay? If I'm working out the momentum on this side, then I want to put plus 0 on the end. Why is that? If I'm working out total momentum on this side. Yeah, this one. Can you see? The 1 kilogram thing wasn't moving. So if you did the calculation for that, you'd get 1 kilogram times 0. Obviously something that isn't moving, doesn't have any momentum. Okay? So the answer on this side is 40. Okay? And the whole point of conservation momentum is it's going to be the same on that side. All right? Momentum on this side is going to be the same. Okay? And you might say, well, how do you know that? How do you know that you can use conservation momentum in that way? Is it necessarily going to conserve momentum? It might not. There's two answers to that question. One is a good physics answer. The other one is a very pragmatic answer. Let's suppose this was a collision that perhaps didn't conserve momentum, because there were some external forces or something. Then you wouldn't be able to do this calculation, so they wouldn't be asking you it. All right? So to be honest, gents, if you're sat down in a GCSE exam and it says GCSE on the front, and you open the paper and they've got a collision going on, just get on with it. All right? If it isn't one that conserves momentum, then you wouldn't be able to do the question anyway. Okay? If you're a bit bothered about this and you think, well, how do you know when things conserve and when things don't conserve momentum? Here's the full answer, which is sort of in the syllabus. This is an example, gentlemen, of a closed system. All right? How do I know I can conserve momentum in this situation? The answer is because it's a closed system. How do I know it's a closed system? What you have to imagine is like a giant plastic bag. Imagine a giant plastic bag around both of the trucks. It goes in between the wheels and the rails. So very importantly, it doesn't include the rails. So it goes underneath the wheels, round the thing completely, and as they stick together, remove off the plastic bag so it comes with them. Now, across that plastic bag, there are, first of all, no unbalanced forces. Okay? And second thing, across that boundary, there is no matter, no material, nothing's jumping out the trucks. If lots of coal fell out of one of the trucks as it made the collision, then that wouldn't conserve momentum, because popping out of the plastic bag, crossing the plastic bag, would be the lumps of coal. All right? So there could be situations where this didn't conserve momentum. All right? Simple answer, not going to happen in your exam paper. All right? If they have two things hitting each other, say work out the velocity, this is how you're going to do it. All right? The physics answer is because it's a closed system, there's no material crossing an imaginary plastic bag around the whole thing, and also no unbalanced forces. A good piece of physics here. If you think about it, there are some fairly big forces crossing the boundary. You've got the weight of the trucks. That's produced by the centre of gravity. That's a force that definitely crosses the plastic bag. So how come we can still tick the first one? How come, if I'd only been listening to half of this lesson, I might say, hang on a minute, the weight of the truck's huge great force, tons, pulling down towards the centre of the earth, that's crossing your plastic bag. How can we say there are no unbalanced forces? There's a reaction force from the rails, isn't there? So, a bit of year 10 physics here. Can you imagine the rails are pushing upwards on the truck? So think about the plastic bag. What have you got? You've got the weight pulling down, you've got the reaction of the rails, and we know those two forces are the same size because the truck isn't, not like in the word moving, it's not starting to rise up, is it? It's not accelerating upwards, nor is it, imagine the rails made of jelly, in which case the reaction force is nothing like as big as the weight, and the truck would start to move down. So the truck isn't accelerating, I'm sure that's what you said, the truck isn't accelerating upwards or accelerating downwards, Newton's second law, so that means the total force must be 0. So these two forces basically cancel each other out, okay? So if you're interested in the physics, that's the reason why this conserves momentum, because if you drew a giant plastic bag around the whole thing, there are no unbalanced forces or matter crossing, it's a closed system, okay? That means the momentum on this side has got to equal 40. That's what you do. That's the trick to this question. That's what's going to get you 3 marks instead of 0, is you work out the momentum before and then just carry it over, all right? Because otherwise you can't do the question, obviously. Okay? What have we got now? We've got 40 is mass times velocity, so it's a bit the other way round now. I know some of you like to do this sort of problem using triangles, so let's do it that way. Momentum is mass times velocity. Don't forget, you don't get the triangles on the equation sheet, you just get the equation. But now, they want V. They want us to work out V. We know the momentum. It's the same as it was before the collision. But now they want us to work out the velocity. What number goes in here and why? What number goes in here now? Look at the picture. It's 5, isn't it? All right. You've now got a mass of 5. I like to think of it in momentum questions. It's not the mass, it's not the mass, it's the moving mass. This mass doesn't really come into the question. All right. Now, how much mass have you got moving? Look at the picture. You've now got 5 kilograms moving along. Okay. So you've now got 40 equals 5 times something. Again, you can do all kinds of different maths ways of working this out, but hopefully you can work out the only number that fits in there is 8. Common sense check. Is it bigger than 10? No, that's good news. So imagine you're driving this 4 kilogram thing, it's quite big, you hit a little thing in front of you that sort of latches onto you. That's going to slow you down. Think about the physics. You've got a certain amount of momentum, but now you've got this extra bit sort of stuck on the front of you. You've got the same momentum, but you've now got to manage that momentum with a bigger mass. The only way that can happen, look at the maths of it, the velocity's got to go down. All right? If you're stuck with your 40, but now your mass has gone up to 5, the only way is to drop your speed down to 8. Okay? Velocity is 8 meters per second. All right? Is everybody happy they could do something like that? Because there's a 1 in 3 chance that will be your exam question. Okay? Any collision question, fundamentally, be much the same. Sometimes they put real numbers in. I mean, we're getting to the thick end of P2 here. They put 5,000 kilograms. They put some proper big numbers in to make it a bit more difficult. Fundamentally, it will be the same thing. The objects will change, but it will be the same thing. Okay? Now, if you're feeling sneaky and you're quite a lazy person, like to do things in your head, there is a very sneaky way of doing this. Beforehand, we had 4 kilograms on the move, and we've now got 5 kilograms on the move. By what number has our mass gone up? Now, don't say 1. What do you have to multiply 4 by to get 5? 1.25. So before the collision, we had 4 kilograms moving. We've now got 5 kilograms moving. Can I convince you the mass has gone up by 1 times 1.25? What would happen if you divided the speed by 1.25? 10 divided by 1.25 is 8. You can actually do it by a very clever bit of A-level physics. Whatever you do to the mass, you'll do the opposite to the velocity. Imagine they were 2 4 kilogram things, what would the answer be? Anyone see? But don't do it all again. Imagine this problem now, but they're both 4 kilograms. Stationary 4 kilograms, moving 4 kilograms at 10.
Would the velocity be 5?
It would. Can you see? Because you're going along at 4, you hit this extra one. What's happened to the mass that's moving? It's doubled. So the speed will halve. All right? Whatever you do to the mass, the moving mass, you'll do the opposite to the velocity. Maths people will be able to look at that equation and see why that works. Now, I would recommend, gentlemen, strong advice here. In the exam, do it this way. Don't sit there looking at it going, well, that's 1.25. That's gone up by 1.25. So divide that by that and that by that and get the answer right. You can do that. You can just write down the correct answer, 8, and you'll get full marks. But if you're doing all of those steps, all of that, and that, in your head, there's a really good chance you're going to get it wrong. In which case, if you just write down the answer, you get nothing. All right? My recommendation would be, do it my boring way, for people who aren't very clever like me. Do it that way. And then, at the end of the exam, go back to it and say, right, I've got the answer 8. Let's just check it. By how much has the mass gone up? Let's divide the velocity by the opposite amount. Correct answer. So can I recommend to you, whatever you do to the mass, you do the opposite to the velocity. Don't do questions that way, but it's a really good check. You can walk out of that exam thinking, I know I've got that question right. That big 6-mark momentum question, I know I've got that right. Other people going, oh, what did you get on question 7? Did you get 8? Did you get 7? Doesn't matter. You can work it out. Use it as a check. Don't do it in your head like I just did, because then if you get it wrong, you're going to get nothing. Okay? Right, let's zoom on then. Let's do an explosion, which is number 2. Okay? Again, there's an opposite situation. 1 and 2 are the opposite of each other, basically. The collision and the explosion are basically the same thing, all right? They're just the other way around, effectively. Okay? Let's have an explosion. Let's have a cannon or something. It's very hard to draw these very well. There's a cannon with a cannonball inside. Okay? And what's going to happen, obviously, is they're going to fire the gun, and the cannon goes like that. And the cannonball obviously goes zooming off. Okay, let's put some numbers in. Let's have this as 5,000 kilograms. So a great big cannon. Let's have the cannonball a bit smaller, although it still hurt you if you hit in your head. 5 kilograms. All right. And let's have the cannonball going zooming off at, I don't know, very fast, 250 metres per second. Okay. The examiners do use this as an opportunity to check if you can do standard form. They actually give you big numbers in tons, thousands or tens or hundreds of thousands of kilograms. Okay. And then expect you to work them out. All right. Wheels back on. Now this is an explosion. You can tell this because the two things start off stationary and go zooming apart. All right. Look back at your skateboard question. Now, when I said, oh, they just change the objects every year, that's no mean thing. When you open your exam paper and it's 3 rabbits and a penguin, you think, what is going on here? I haven't seen this before. This is the skill, gentlemen. If you can look at the question and think, well, actually, factually, it's just like an explosion question, then you're just going to get all the marks. Okay? So I've got a cannon firing a cannonball. They tend to be out of favour these days. You don't tend to get questions like that, about guns and cannons and things, but it's a nice, simple example. All right? Now, exactly the same thing. What's the piece of physics that's going to allow you to do this question is exactly the same. This is an example of conserving momentum. Okay? So whatever momentum we come with on this side is going to be the same on the other side. Okay? And in actual fact, the momentum on this side is very easy because it's 0. Before they fire the cannon, there is no momentum. There's the cannon, there's the cannonball. Hasn't been fired yet. 0 momentum. And that means that the total momentum on this side is going to be 0 as well. Okay? Both sides of the explosion, the momentum is 0. Okay? And at first that seems a bit strange, but like I said, once you've seen how it works one time, you'll be able to work out what's going on a second time. All right? All explosions work in much the same way. Okay? You could have the two masses the same. It'd be a pretty stupid kind of cannon made of 2 halves of the same mass. So you fire it and kill yourself, and then a few seconds later kill your enemy or something. So generally, the cannon is much bigger than the cannonball. You'll see why in a minute. Okay? Well, this is a bit odd. What are they asking us? They're asking us about, normally, in exam questions, they generally ask you, they tell you how fast the cannonball goes, and then they say, how fast does the other object go? In what word might we use in everyday speaking for that? This movement backwards, it's called recoil, isn't it? So they might say to you that when the cannon is fired, then when the thing's fired, the cannon recoils. In your skateboard question, I hope you can look at that now and see it's the same thing. All right, you've got the cannonball, which is the skateboard goes flying off at some tremendous speed, and by doing that, if you stand on a skateboard and you flick it out from under you, you automatically send yourself backwards by conservation of momentum, as we're going to see in a minute. Okay? Good rule of exam questions, gentlemen. If you're stuck and you think, I don't know what to do next, most exam questions, certainly at GCSE, a really useful rule is work out whatever you can work out. There isn't normally much room for manoeuvre in these questions, so you might sort of lose speed here and think, oh, not quite sure. I know it's naught, but how does that help me? Well, look at these things. Can we work out the momentum of the cannon? We can't, because we don't know how fast it's going. In fact, that's what they're asking us to do in the question, so that's not going to start. What about the cannonball? We know it's 5 kilograms. We know it's moving at 250 metres per second. If you get to this point in the exam and your brain stalls and you think, I don't know what to do, well, what could you do? The only thing you can work out is that, and that, in fact, is the next step. So next thing we're going to do is to work out the momentum of the cannonball. Okay? Now, the mass is 5 kilograms and the velocity is 250 metres per second. Okay? 5 lots of 250 is 1250, obviously. 1250, horrible units again. Kilogram metres per second, there we go. So the cannonball has 1,250 units of momentum in that direction. Okay? Now, what you've got to think to yourself then is basically how we're going to make this work. Because the cannonball has a momentum of 1250. The total's got to be 0. Even after it's fired, the momentum is 0. Because again, it's a closed system. Here's my plastic bag. It's an extremely stretchy plastic bag. So when you fire the cannon, the plastic bag stretches so the cannonball is always inside it. It's quite a strange sort of plastic bag, but I think you can see, exactly like last time, there's no unbalanced forces and there's no matter. If the bag expands to keep the cannonball inside, the cannonball never crosses the plastic bag. And also there's some very big forces here inside the gun. There are some enormous forces, but the rule is for a closed system, no unbalanced forces. And you might say, what about the explosion inside the cannon? Well, those forces don't cross the plastic bag, and of course they're perfectly balanced. As hard as the gun pushes the cannonball forward, the cannonball pushes the gun backwards. Those two forces, Newton's third law, are exactly the same size. So again, a big tick there, closed system. Feel free to ignore that last 30 seconds. If it says GCSE on the front of your paper, you can conserve momentum. All right. Otherwise, how could you do it? Okay. So we've got to think to ourselves, momentum of the cannon has got to go in there. Afterwards, this is why it's like the collision backwards. Afterwards, you've got two moving objects. They've got to add up to 0. This one is 1250. Hopefully, I can convince you the only number that's going to go in here is minus 1250. All right. This will have, you can put it on here if you want to, that's got plus 1250 units of momentum. That goes backwards with minus 1250. Okay? Giving a total of 0. All right? They had no momentum before. They are a closed system. Even after it's fired, it's still a closed system. And so the momentum must stay at 0. So whatever momentum that cannonball goes flying off with, the gun will come backwards. All right? And certainly in the time of Lord Nelson, people like that, when we used to have ships with big sort of metal cannons firing cannonballs, it was quite likely in a battle to lose quite a few of your own sailors. If they were stood in the wrong place when the gun fired, the cannon would recoil backwards, not very quickly perhaps, but it would be really clear it's carrying the same momentum as the cannonball. And it's certainly enough to, cause you serious injury. So very important, this bit, equal and opposite momenta. Right, now then, how does that help us? Well, it means we've now got, for the cannon, we now know minus 1250's got to equal m times v. All right? Although it's some of the hardest physics in P2, the actual maths of what you do is normally quite simple. Just momentum is mass times velocity. Which ones do we know now? We know the momentum. It's got to be minus 1250 to balance the 1250 of the cannonball to give us a total still of 0. That's going to equal mass times velocity. We were told the mass of the cannon at 5,000. And I'm sure you can all work that one out in some way. All right. Minus 1250 divided by 5,000 is going to give us a velocity. Maybe I can do that. I pick numbers that aren't nice. Sorry. Minus 1250 divided by 5,000. Minus a quarter. Thank you. Minus 0.25. Don't forget to be meters per second. There's your answer. Okay. The answer comes out as minus 0.25 meters per second. Okay. That tells us that the cannon must move at 0.25 metres per second the opposite way, all right? important word to put in the margin somewhere is that velocity and momentum are examples of vector quantities. I'm sure you've done that in maths. Vector quantities are things that have a direction. Okay? Very importantly, and they can be quite sneaky on this in the exam, they can just say to you, work out the velocity of the cannon, and you put down 0.25, and you will lose a mark. When they say what's the velocity, some of you have asked me at several points across the 2 years, what's the difference between velocity and speed? Well, here's the difference. Velocity is a vector quantity, and so it has a sign that tells you which direction. Good way to contrast that, speed doesn't. Speed is not a vector. If I drive this way at 30 miles an hour, the speedometer says 30. If I drive this way at 30 miles an hour, the speedometer says 30. The thing in the car with the numbers on is a speedometer, and speed is not a vector. So you need to be really careful. In the exam, if they say what's the velocity, you have to put a plus or a minus sign to show the direction. So if you put 0.25 for this question, you would lose a mark. The velocity, gentlemen, is not 0.25. 0.25 is that way. Plus velocities are in that direction. Look at the cannonball. Minus 0.25 in the opposite direction. So please put an exclamation mark or something there. As I said, we're getting to some of the hardest physics you're going to do. There's attention to detail here. You've got to have the minus sign to show it's going the opposite way to the cannonball. Right, let's go back to our route map, gentlemen. This is where we're going. If you look at the question and you think, gosh, this is a collision of some kind, that's how you do it. If you have looked at the question and you decide it's a kind of an explosion-y question, then I've just shown you how to do that type of question. It'll be exactly the same. If, however, you look at the question and you think, gosh, that's not conserving momentum, and that's really quite common. As I said, here's an object. If I drop it, that hasn't conserved momentum. It had plenty of momentum when it was sailing downwards, but now, having hit the table, it has not conserved momentum. That's when you use the quantity called impulse. All right? Impulse helps you to deal with situations where, and this is number 3, where momentum is not conserved. All right? Now, momentum not being conserved is quite common. It happens all the time around you, unlike energy not being conserved, which is almost not ever happening. Okay? So if you decide the question doesn't conserve momentum, then you don't do that, you don't try and conserve momentum. Momentum before equals momentum afterwards. Imagine trying to solve this problem with momentum before equals momentum afterwards. Well, it doesn't. Momentum before is such much, momentum afterwards is 0. It's clearly not conserving momentum. That's when we use the idea of impulse. Now, again, we're not going to write complicated notes on this. Let's just have a go at an example of a question. And I have to say, one that appears in exams an awful lot is somebody sat in a car normally. A car a bit dotty. Somebody in a car having an accident, all right, I have to say is a really common example. If you look back over past exam papers, look up the impulse questions, they'll be easy to find. They'll be right at the end of the paper. Impulse questions, gents, are some of the hardest questions that you do, okay? If you get them, they're nearly always to do with some sort of accident or road safety or something like that. Because again, that ticks lots of boxes for the exam board. It makes the question paper look much more relevant. But you will find an awful lot of examples of impulse asked to do with road safety, and this person is going to, they're going to drive into a wall. Okay? Now, if you think about that, there's no way that conserves momentum. They're chugging along at top speed, and they hit the wall, and they haven't conserved momentum. And that's why it hurts, because the way that you don't conserve momentum is using a force. If I'm going along at a certain speed quite happily, and suddenly the wall comes up, and I stop, that hurt. Why did that hurt? I've just experienced a large force. It's forces that stop you conserving momentum. Okay? You might have learned that lower down the school as force is mass times acceleration. This is just another way of looking at it. All right? When does momentum not get conserved? It's when forces come along. Okay? So I'm going along with my momentum quite happily. I don't conserve momentum because the wall stops me doing that, and that means I've experienced a force. All right? The impulse equation simply links those two things together. Okay? And the equation for that is basically change in momentum Now there's the first thing, look at that, change in momentum. Where did that appear in the last two? Nowhere, because in those two, momentum was conserved. You can see straight away, this is the equation for when momentum is not conserved. Change in momentum is equal to force times, sounds a bit of an old-fashioned way of writing it, but it's important, I think. It's the time for which it acts. This is called the impulse equation, because force times time is called impulse. Change in momentum is force times the time for which it acts. Okay? So if I use 6 newtons on something, there's something moving along, I get 6 newtons and I push it for 3 seconds, I will change its momentum by 18 units. Okay? The amount of momentum change is the size of the force, let's put the units in newtons, and the time in seconds. Okay? Now, if this was actually happening, then I might ask you how much force is there from the wall in stopping the person. How much force does the person experience? Okay? Let's put some numbers in. Let's have the person at 50 kilograms. Let's have the speed, I don't know. They're zooming down the motorway at 40 metres per second, 90 miles an hour, and they're 50 kilograms. Okay? And let's suppose they don't have a seatbelt. Many, many times have I seen impulse questions look like this. Do you remember the clip we watched the other week, the Futurama clip with the spaceship? And they were going to crash, weren't they? So they all put their safety belts on, apart from Bender, who went flying through the windscreen, don't know how he did that, and landed on the floor. Okay? So imagine you're having, and certainly when I was your age, new cars had to have seat belts. You didn't have to wear them. And many people were finding that people were being killed in quite low-speed road accidents because the thing that was stopping them, if you think about it, imagine you're sat in the passenger seat and the car suddenly stops and you haven't got a seatbelt on, you would tend to go forward and you would stop yourself using your skull and the windscreen. Or if you went through the windscreen using the bonnet or the road or something, and those tend to be quite short duration impacts. If you smack your head into a windscreen or into a bonnet or to the ground or something, that tends to be quite a short time. So let's suppose this crash, if you like, takes place in just 5 milliseconds. And again, we're at the top end of P2, gentlemen. This is higher tier GCSE. They don't give them away. Even though it's difficult physics, they'll slip in the odd wrong unit just to sort of mess you around. 5 milliseconds is obviously 5 over 1,000 or 0.005 of a second. I hope you won't fall for that one in the exam. Okay? So this is an impact where there is no seatbelt. All right? You're going along at this speed, happily toddling along, then suddenly like that, and it's all over very quickly. All right? Let's put the numbers in. Change in momentum. Don't forget momentum is mass times velocity. So it's going to be 50 kilograms times, what are we doing, 40. We're 50 kilograms, we're doing 40 metres per second, and suddenly it's all gone. That means change in momentum is 50 times 40. Okay? And the force we don't know, because that's what they're trying to ask us to work out. The time for which it acts, how long does the force have to slow the person down? Well, they're not wearing a seatbelt, so it's just the brief impact between their neck and the windscreen that is the time that it acts for. That's 5 milliseconds, 0.005 of a second. 50 times 40 is 2,000. That's going to be F times 0.005. I know it's really horrible, complicated physics, but it's normally just momentum is mass times velocity. What do they want this time? They want the force. So a bit of rearranging here. It's going to be 2,000 divided by 0.005. Before you touch your calculator, what size of number are you expecting? Big. 2,000 divided by, I hope you know now, if you divide by a number less than 1, you end up with a very big answer. 2,000 divided by 0.005. Anyone got a calculator? What does that give us? 400,000, thank you. That gives you 400,000 newtons. Or if I'm the examiner, I want the answer in kilonewtons. Just to annoy you. 400,000 newtons. That's the weight of about 40 tons. And these numbers, normally the numbers I make up on the board are stupid, but actually these are perfectly reasonable numbers. If you had an accident at 90 miles an hour and you weren't wearing a seatbelt, the force you can expect on your neck is about 40 tons. You're not going to survive. Okay, so next to that you can draw grumpy face. That's not good. All right. The scary thing about this is if you drop the speed down to say 30 miles an hour, say 12 meters per second or something, this is still very big. Why are we getting such big numbers here? What's causing that? That's a reasonable number, that's a reasonable number. What's causing the force to be so big? It's this. What's ramping up the force by a factor of 1,000 odd every time? It's this number, isn't it? Okay. So what I'm going to do now, you've got a choice. You can either do a second example. I'm going to do a second example in red over the top. You can write it out on the opposite page or something like that. It's up to you. But you're the guys who need to practice this and to see lots of examples and to get good at it. I'll leave you to decide what you want to do in your book. But what I'm going to do now is to make some changes. What we're going to do is we're going to fit the little guy with a seatbelt. Okay? Now that means when he comes up to the accident starts with not just the seatbelt, we're also going to put him in a car which has, on the front of it, a crumple zone. You might have heard about this. All modern cars have to have a decent amount of crumple zone. Every new car design before it's allowed on the road has to be crash tested. Okay? And that means they pick one at random off the production line, they smash it into a wall, and the front of the car literally has to fold up like a Coke can. It's really annoying, actually, if you have a low-speed impact. I've been in a car accident where we're doing literally no more than 20 miles an hour and just touched the car in front, and the whole of the front two wings, the bit across the middle, the radiator, everything just folds up, and the radiator split and the car couldn't move and it cost an absolute fortune. And we're doing it at like a tiny speed. The fronts of cars, if you look at them next time you go past a car, look at the wing, things like that, they're made of a metal, they're made of quite thin metal, and they are designed to crumple up. Okay? So think about the accident now. I'm driving along in the car, I go along, and I have an impact on this. Well, first of all, the car takes some time to crumple up. It takes, I don't know, 3/4 of a second to crumple up the front of the car. Then the bulkhead, which is normally behind the dashboard, hits the wall. And then I start to go forward, but I don't just stop like that. I go forward in my seatbelt and then go back again. So if you can imagine that, I'm sure you've seen crash test dummies and things doing this. Imagine the slow thing like that. I've exaggerated a bit, but let's suppose that changes the impact time to 2 seconds. So now, it'll all seem quicker because you're adrenaline and stuff like that. You go into the wall, the front of the car folds up, then you start to move, then the seatbelt pulls you back, and the whole thing maybe takes 2 seconds. Okay? Now, let's go through the equation. You can write it out again if you want maximum practice from the lesson, or you can just watch, it's up to you. What are we going to change in here? That stays the same. There was a question a few years ago that asked you to explain how this works, and that was a key point. How much momentum has the person got to lose? Exactly the same. They're still 50 kilograms, they're still doing 40 meters per second, and they're still stopping. They're still losing 2,000 units of momentum. So this 2,000 isn't going to change. Okay? What is going to change is that time. It won't be 0.005 a second now, which was when you had no crumple zone. So like a traditional sort of 70s car with like giant box girders for wings and stuff, and no seatbelt. Then literally as the front of the car hit the wall, you'd be moving immediately, and then you'd be onto the windscreen. Okay? That's going to change to 2, which means that's going to change to 1,000. The force is now just 1,000. Okay? 1,000 newtons is the weight of 100 kilograms. That's probably a couple of sixth formers sitting on you. Now, I'm sure it's happened to all of you. We've all done it, haven't we? Out in the playground, you know, a couple of sixth formers just sit on you or something like that. That's not nice, and it's unpleasant, but it's not going to kill you probably. Well, not often. And 1,000 newtons, that is very... Can you put a smiley face next to that? That is extremely survivable. You're going to have a sore neck. You might break your collarbone or something, but you're very likely to walk away from that. Very good. Finally, gentlemen, very good physics question a few years ago on this, and they asked you to do pretty much this calculation, and then they said to you, explain why the force is lower. 2 marks. So they made you do the horrible calculations, but then they said, explain for 2 marks why this force is now lower. What were the 2 pieces of physics they would have been looking for? Yeah, you're getting rid of the momentum more slowly. So the time for the accident is taking longer, and let me help you out by rearranging this equation. If I rearrange this equation for force is change in momentum over time taken. The force is lower because the time taken was longer. Do you see how it works? Force is change in momentum over time. If you make the time longer, that's what a seatbelt on a crumple zone does. The force is going to go down. What was the second mark for? That's it. So the full answer, many people got one. Many people got one because they said the time got longer. The time got longer and you were losing the same amount of momentum in a longer time. Force, gentlemen, final thing you might want to jot down. Force is linked to how quickly you lose momentum. Let me say that again. Force is linked to how quickly you lose momentum. Do you see? Because it's changing momentum over time taken. If you lose your momentum slowly, yeah, that's a very small amount of force. If you lose your momentum quickly, that's a large amount of force. All right? And that's the 2-mark answer at the end there, the 2-mark explain question. The force goes down because you're losing the same amount of momentum, but you're not doing that, you're doing that. Okay? And that's a typical example of an impulse equation.